started. So the first thing I'm going to do is I'm just going to install some software on my Linux installation that's on right now. So I've already done it. This is the instructions are in the slides, which I'll show you in a second. Okay, so I've installed Pac-Man for the console. Now, it's important to remember that the console was never intended for this sort of thing. Basically, the console is intended, you type something in, you press enter, something happens. The fact that someone got Pac-Man to work on here is kind of crazy. Oh, hang on. Got to make my window a little bigger. There we go. There we go. And so you can now play Pac-Man on your console, which is kind of stupid and hilarious at the same time. If you want to quit, it's just Q. So if you feel like playing Pac-Man in your console, go ahead and install that and have countless hours of fun. All right. So the topic of today's lecture is, there's a couple of slides on the history of Linux and Unix to set the context for everything that we're doing. And then we're going to talk about the file system. All right, so there's the instructions for installing Pac-Man if you want them. It does work on Mac if you have Brew installed. Right, so if you're following the, if you looked at the course instructions on getting started, if you look at the Mac section, it tells you to install this thing called Brew. And then using Brew, you can install a whole bunch of other software. If you're on Linux, just do sudo apt-get install Pac-Man for console, and away you go. All right, brief history of Linux. So I think I told you about this last class. So when people say Linux, they actually mean GNU Linux most of the time. Linux is what's called the kernel of the GNU Linux operating system. So the kernel is the part of the operating system that provides an interface between the hardware and software. Right? So there's lots of other parts of your operating system. The kernel is the thing that talks to the hardware. Linux is actually modeled on what's called the Unix kernel. So if you click that link, and hopefully this skip verification. Hopefully this works. All right. So first of all, there's this picture over here, which you probably can't see very well at all. Shift. Oh, that's not going to work. Sorry. So on when you have a chance to look at this picture, this is actually showing you the evolution of Unix to Linux. Unix starts way back up here in 1969. Over here on the left-hand side, this is where your Linuxes are. Mac is over here. So Mac is actually a Unix descendant, although it's pretty far removed. Well, that's not true. It branched off from Unix back here in 1995. If you actually look at what's on this page, rather than just the picture, you can read about the history of Unix here. You'll see over here there's a bunch of names of some people who developed the Unix operating system. So Ken Thompson, Dennis Ritchie, Brian Kernighan, Douglas McElroy. If you look at all these people, I think 3 of the 5 that are here, they're all Turing Award winners. So the Turing Prize is the highest prize you can win in computing science. The developers of Unix, many of them are actually Turing Prize winners, and they're responsible for a lot of the software that's used today. Who is that? Sorry, someone's trying to call me. All right, so I'm actually not going to go through this page. If you're interested in the history of if you're one of these people who are interested in history, that makes for an interesting reading. I think there's a link somewhere in the notes, too, that takes you to a different page that talks about it. So Unix is an operating system that was developed in the 70s at Bell Labs. It became one of the first portable operating systems. So portable means you can use it on any computer. Well, not almost any computer, because it was mostly written in C. So before Unix came along, whoever manufactured the computer would write an operating system specifically for that computer. You also have to remember that back in these days, computers are not these things that sat on your desk. They basically take up a whole room or part of a room, and it's basically this giant cabinet full of electronics. Right. Now the problem with this thing is that Unix was very expensive when it was commercialized. So a license in those days was $20,000 US. That's for one license, which is the equivalent of about $120,000 today. So imagine paying $120,000 for Windows or Mac OS. No one's going to do it, right? Way too expensive for individual users. I think universities got a discount. I think they got it for like $250 or something like that. Anyway, not important, right? It was very expensive, and largely proprietary at the time. So in 1983, this fellow by the name of Richard Stallman started the GNU project. The aim back then was the goal of creating a free Unix-like operating system. Free because if you wanted to use a computer, you don't want to fork out thousands of dollars just for the operating system. And so him and some other people started to develop the tools you needed to develop an operating system. The funny thing is, they never actually got around to developing the kernel itself. So they managed to build the tools. So they built the compiler, a bunch of command line tools like the ones I've been showing you. They were responsible for implementing. And they never got around to making the kernel. So the kernel for GNU is called Herd. It's still not done today. They started in '83. Now, the reason it never got finished was because, one, it's hard to write a kernel, but two, in 1991, this guy named Linus Torvalds came along. He's a graduate student, so he's a master's student at some Finnish university. He decided he wanted to write his own Unix kernel for the 8386 processor. So this is the predecessor of the Intel chip that you have in your computer, that many of you will have in your computers. Right? Mac now makes their own chips. Right? And so he managed to create the kernel part. And the way he did it was he took all the tools that the GNU project developed and used those, the compiler and so on and so forth, to write the kernel. And so you mash the two together and you end up with GNU Linux. Right? And that's the Linux that we now know today. Right? So today, Linux is dominant in cloud infrastructure and supercomputing. So the top 500 supercomputers in the world all run Linux. Cloud, so if you Google what does Google use, or what does Netflix use, or what does Facebook use for their infrastructure, it's all Linux or something called BSD, which is another free Unix derivative. Android is a Linux derivative. It runs on 70% of smartphones in the world, about half of the smartphones in North America. Embedded systems, your router probably runs Linux if you have a router at home. Uncommon on the desktop, so despite a lot of effort by many, many, many people, Linux never really took off on the desktop. So I think globally it's like 2 or 3% of users use Linux on the desktop. Now, why do they use Linux in this cloud infrastructure and supercomputing? Because the way this stuff works is it's a whole whack of computers in a room. None of the computers actually have a monitor. Right? So it's just racks and racks and racks full of computers. And so to access one of these computers, what do? Well, you don't go walk in with a monitor and plug it into the computer. Right? You remotely log into the computer and use a console to access the system. And you can actually do that here. Right? So if you can actually log into CASLab remotely. Right? So if you look at the CASLab documentation for the department, there's instructions there on how to remotely log into CASLab and use one of the CASLab servers. Okay, you might see something called POSIX. So POSIX was an effort to standardize operating systems. And so they listed a bunch of stuff that every operating system should have if you wanted to have some sort of interoperability between the operating systems. It's still an evolving standard today. So every once in a while you might see this term. All commercial Unixes are POSIX compliant. Mac OS is POSIX compliant. Linux is mostly POSIX compliant. All right, so that's your very, very, very quick history of Bash and Linux. There's a notebook for you to read if you want to read a little bit more, and inside that notebook there's links to articles that actually give you the whole evolution of Unix and Linux. All right, so this thing we've been using is called a Bash shell. Right? So that's what a terminal is. This is what a terminal used to look like. Right? So a terminal is basically the way you interact, or the way you used to interact with a computer. Right? So back in the old days, a terminal was either a purely electronic or an electromechanical device for entering information into the computer and for getting information back out of the computer. Right? So for data input and output. On the right, that used to be how you interacted with a computer. You have a keyboard, you would type something in, you'd press enter, you would wait, and then that's a printer back there. It would actually print out the output from the computer. Right? So that was way back in the 70s. Sometime probably late 70s, mid 70s maybe, they managed to get a, I guess, an optical terminal, right? So you'd get a TV, what looks like a TV. Basically, that would be the way you would get output from the computer, right? So basically, that terminal there is similar to, oops, sorry, is here. So the modern day equivalent of a terminal is this thing here, right? So this is what's called a terminal emulator, right? So it emulates the old electro-optical or electromechanical device that you used to have to use, right? Type something in, press enter, you get output on the terminal. Oh, that's interesting. Sorry, that's not what I wanted to do. Okay. Right, so in this course, you're going to be using a software program called a terminal emulator. Right? Now, inside that emulator, so the terminal is running a program called a shell. So the shell of your terminal is just a piece of software. It's the thing that interprets the text that you type into the terminal, right? So when you type something in and press enter, the terminal sends the text you sent to the shell interprets it and tries to do something with it, right? Where does the text come from? Well, it comes from the terminal. Right? And you have your choice of many, many, many different shells. Right? And so the quote-unquote standard Linux shell is called bash. Right? On Mac, this standard shell is now called ZSH, the Z shell, which is super inconvenient for me because now I have to tell you how to upgrade bash on your Mac. And there's actually many, many different shells. Right? Windows has its own equivalent. Right? If you've used PowerShell or the CMD prompt on Windows, those are all examples of shells. Right, click that link there, you'll get a list of, you'll get the Wikipedia article on shells. Right, bash is the born again shell, right, and it replaces the older born shell from Unix. Right, and that's the default login shell for most, but not all Linux distributions. Right, so it's important in this course that you're using a modern version of bash. Right, so bash is the version's now up to 5. You need to use version 4 or higher, which on a modern Linux installation you'll have. The problem with Mac is Mac got stuck at version 3 point something, and they never upgraded it past version 3. And on a modern Mac, you can't upgrade it yourself anymore. So you have to install a separate version of bash on a Mac and then use that separate version. Okay. Fortunately for Mac users, the Z shell is pretty similar to bash. So even if you mistakenly use the Z shell instead of the bash shell, you're probably going to be okay in for most things that we do in this course. But you should try to use the bash shell if you're a Mac user. All right, the file system. So I want to go to this link here, which is actually in a notebook. So I'm just going to go to the notebook here. Where is it here? Okay. Okay, so this is the file system notebook that you have access to. Can you read this at the back, more or less? Kind of good? Okay. So there's something pretty important that you need to know about Unix. And Linux is a Unix derivative, so you need to know that about Linux. So in Unix, there are these things called, well, on any operating system, there's these things called files, right? So you know you've got a PowerPoint file or a Word file or a text file or something like that, right? The exact same thing exists on a Unix operating system. There's files, right? As far as Unix is concerned, all files are just bags of bytes, right? And so in other words, it's just ones and zeros, right? And it has nothing else associated with the file. If you're a Mac user, that's not the case, right? Mac actually has a pretty sophisticated file system. You have the file where the data resides, and then you have another file associated with the file that lets you do all sorts of interesting and neat things, right? That's not the case in Unix, right? So in Unix, there's no way to store information about the file, right? You just got the file itself. And in Unix, everything is what's called a byte stream, right? So this is important. This is what you should keep in mind as we work through the first 5 weeks of the course, right? So everything's a stream of bytes, and all that means is that data flows as a sequence of ones and zeros, right? And similarly, when a program or a command needs to write output, it writes out a stream of ones and zeros, right? So everything's a stream of ones and zeros, and that's the underlying metaphor of everything that's Unix, right? Which actually is a problem in today's day and age because you can't represent a lot of data as just a stream of bits anymore, right? all the things that you're going to use in this course, right, they all come from this metaphor where everything's just a stream of data, right? So the examples I showed you last day, right, where you would type in fortune and then send the output of fortune to another command, right? That works because everything in Unix is just a stream of data, right? Fortune outputs a string as a stream, right? Another program can read that string as a stream and then do something with it, right? And that's true for even the hardware on your operating system, right? Which is kind of cool, although it's limiting in some respects too. All right, so your file system is the part of the operating system that controls how data is stored and retrieved, right? So basically, the file system is usually associated with your hard drive, right? Hard disk, your CD-ROM, if you have one, you probably don't have one anymore, right? Magnetic tape, if you're still using that, your USB drive, whatever, right? Normally, the file system is associated with that, right? On Windows, you've got 3 file systems that are still in use, right? Your USB sticks are probably formatted as FAT. Your operating system itself, your hard drive is probably something called NTFS, right? Mac uses the AFS, the Apple file system. Linux has got, I don't know how many, dozens of file systems that you can pick from, right? Okay, so a device is a physical piece of hardware that can store files, right? i.e. a device is like a USB flash drive, a hard disk, or something like that, right? Now, everything to Unix is just a stream of bits and bytes. So any of your storage devices on a Linux computer is actually represented by a file, right? When you want to write to your device, you write to the file, right? When you want to read from the device, you read from the file, right? And so the file turns out to be, it actually is a file in the file system. You can go onto your file system and look for this file, and you can find it if you know where to look for it, right? So your devices are represented by what are called device special files, right? So your device special file, that's your interface to your device driver, right? So everything that's all at the low level, right? The operating system doesn't necessarily, well, programs that need to write to the, need to read or write to your hard drive, right? It looks like you're just writing to a file, right? The operating system takes care of all the nitty-gritty stuff of dealing with the actual device, the actual hardware itself. So these device special files are how Unix models devices as byte streams, right? And this means that if you want to write to a CD-ROM, right, it's the exact same thing as writing to a hard drive as far as the user is concerned, right? They just write to a file when something happens. All right, so as far as your device is concerned, right, so your hard drive is just, so the contents of a file is just bits and bytes, right? So when you write a file, it's just ones and zeros, right? It's just information. Now, exactly how does the operating system represent your storage device? Well, that's complicated, right? So we'll make a really, really, really big simplification, right? So imagine that our operating system pretends or provides the illusion that your disk drive is just a big, giant array, right? So when I want to write information into this hard drive, I need to write into the array. When I want to read information from the hard drive, I'm going to read from the array, right? This is a huge simplification, but it's actually not a bad one, right? Okay, so this, back up. So that gray box there, that's picturing an empty array, right? So I have an empty hard drive. Now, I write a bunch of files to my array, right? So the red part of the array, that belongs to one file, right? The green part of the array, that belongs to a second file. The blue part of the array belongs to a third file, and so on and so forth, right? Again, a huge oversimplification, but sufficient for our purposes, right? Now, if your operating system represents your file system this way, right, the operating system has to record information for each one of these files, right? So what information does the operating system need to store so that it knows where the contents of a file can be found, right? So if I want to know where the contents of file 1 are found, what do I have to store, right? This is just a big array, so what do I need to store? It's not hard, not a trick question. Anybody? Yes?
I guess however many dimensions it would be, like you have to have like one piece of information for each.
Yeah, so for each file, you're going to store what exactly?
Information.
Yeah, like what exactly?
Location.
Okay, what about, so that tells you, presumably the start of the file, right? So you want to write the index of the start of each file, right? That makes sense? What else do you need? You need something else, yeah?
Metadata and like.
Yeah, this is all metadata we're talking about. But yes, you're right. But what else do I need to know about the file? I know where it starts.
When it's created.
I need to know its size, right? Or where it ends, right? At a minimum, this is what I need to record, right? So does your file system record this? Yes, it records this information, right? What else is useful? So, I mean, you've all looked at your file browser, right? What else did your file browser tell you about your files? Tells you the name, the size, what else? Yeah? Yeah?
The data is last modified.
Yes, right? Tells you when it was modified, right? Yeah? Last access, right? A bunch of other things, yeah?
The type of file.
Type of file, yeah. So all this information might be stored by your operating system, right? Because all this stuff is useful to users, right? At a minimum, though, you need to know where does the file start, where does it end, right? So not surprisingly, there's a data structure that stores all this information, right? The data structure is called an inode in Unix, right? On Mac, no, Mac's the same thing because Mac is a Unix derivative. Windows, it's different, right? But on a Unix system, the data structure that stores information about files is called an inode, right? So the inode records stuff like what device is the file on, right? Is it on my hard drive? Is it on my optical disk? Is it on my second hard drive, et cetera, et cetera, et cetera, right? It stores something about, some information about the file type. It says who owns the file, right? That's useful to know, right? How big the file is, right? When was the file created? When was it modified? When was it accessed? And a lot more, including where do you find the file on the hard disk itself, right? So when you store a file on a hard disk, it's actually stored in a whole bunch of different places. It's not stored in a contiguous chunk, right? But we don't care about that, right? What do you need to know? You need to know that the inode is the data structure that stores information about files. Okay, so if an inode is a data structure that stores information about files, right? The operating system has to store the inodes somewhere, right? So somewhere there's a list or an array of inodes, right? Corresponding to every file on your operating system, right? How you can store the inodes, you can store them however you want, right? The way Unix does it is it assigns a unique integer number to each inode on a device, right? So in other words, you can just think of the inodes being stored in an array, and the inode number is just the index where it's stored in this array, right? It's just an identifier, right? So it's just this integer number that says what the inode is. Right? Technical detail, different devices can have the same inode numbers, right? So your hard drive might have inode 5, your USB key might have inode 5, right? So 5 is not a unique inode identifier, right? The identifiers are unique per device. Not really important, right? So this is interesting, back here. If you look at that list of stuff that I showed you, right? The file name is not stored in the inode. Right? Which might seem weird to you, right? And say, hey, I mean, the file name's kind of important, right? The file name is associated with the file, right? I should probably store that information somewhere. It is stored somewhere. It's not stored in the inode that, for the file, right? So a directory or a folder, right, is just a file, right? So it's another type of file. It's not the same as a regular file, right? It's a directory file, right? The contents of the directory, it's just a table, right? The table is, right, column 1, the inode number. Column 2 is the file name associated with that inode, right? So the images directory or folder, right, on the computer that I was using when I generated this table has this inode number, right, 662,400, right? Could be 1, it could be 0, it could be 999, it could be anything, right? The animals.txt file, right? It has the inode number 662,411, right? Arrays.ipynb is 657,898, right? So all these files which are unique, right? They all have unique inode numbers. Oh, why do I have the, I don't know why I have images there twice. Images shouldn't be there twice. All right. Hard links. Okay, so a hard link is a directory entry that maps a file name to a file, right, or an inode. So on this page here, on this table here, right, each entry you can think of as being a hard link, right? So images, that's the directory associated with inode number 662,400, right? Animals.txt, that's the file associated with inode number 662.411. Right, whoops, sorry. That's what a hard link is, right? So if you have a file on your disk drive, it has to have a hard link, right? It has to have a name. It has to have a mapping of a name to an inode. Right? Now, in Unix, you can create hard links to the same file, right? So in other words, I've got this file called animals.txt, right? It has the inode number 662.411, right? It's possible for the user to create another file, I don't know, just call it animals, right? And have the same inode number as animals.txt, right? So now I've got two files, or two names, that point to the same file, right? This is like using Java or Python and having two references that point to the same object, right? So what does that mean? If I use either file name to open and edit the file, and I change the file, right? Then when you open it with the other file name, it sees the change in the file, right? So these links, or these file names, are actually just links to data, right? They're just references to inodes. All right, so keep that in mind. We're going to talk about hard links a little bit later on. Yep. Yeah, so the question is doesn't that cause a problem when possibly rewriting the file, right? The answer is, if you have a hard link, then it's indistinguishable which file actually belongs, it is indistinguishable whether or not there's only one file, right? You write to it using one name, and you look at it using the other name, the change is there. Yeah. You can even open it up with both names at the same time and write to the data at the same time. All right. So that's the lecture slides for today. Now I'm going to pop open that file system notebook, and I'm going to show you how to navigate through your file system. All right. So in the notebook, when you pop open the notebook, so everything I just talked about is actually in the notebook, right? So if you are reading the notebooks, just all the information is there for you in another way, right? So I want to scroll past all this stuff. And I want to go to the file system hierarchy standard. So Unix, and I guess, well, I'm going to say Linux for now. So Linux says that there's something called the file system hierarchy standard, and it defines what your file system should look like, right? So it defines what the directory or what the folder structure of a standard Linux distribution should look like, right? So what you need to know right now is that this standard says that at the very top of the file system, there has to be a folder called /. Right? So that's the name of the folder, right? It's actually called /, right? And that's the folder that contains all other folders in the file system, right? So the Linux file system, there's one, and it's hierarchical, right? Windows is different, right? Windows, you can have a C drive, a D drive, an E drive, and they all have their own separate file systems. On Unix or Linux, everything gets mapped to a single file system. Right? At the top of the file system is called root, right? Or /, right? Okay, so I want to go to that root directory, right? And so the way you go to the root directory is you use the command called cd, right? So in Linux or Unix, there is the notion of what's called the current working directory, right? So that's the directory in which your shell is currently operating in, right? cd is the command that changes directories. Right? So if I say cd space /, that says, please change the current working directory to the root directory. Right? So if I'm in that cell and I run the cell, right, nothing happens, right? Which is the norm for most commands in Linux. Right? So if a command doesn't have anything interesting to say, then normally a command says nothing. Right? So if you tell if you ask the shell to switch to another directory, and that directory exists, it simply switches the directory and nothing gets output. Right? If you want to see it in action, oh, sorry, what did I just do? Okay, that's, I did that. Right, so you can do it in the terminal as well. This one, please. All right, maybe not, just a second. Okay, so in the terminal, right, you can just write cd /, press enter, and you'll be in the root directory. Notice that if you're in the terminal, right, on many current versions of Linux, right, or Bash, sorry, it'll print out the working directory to the left of the prompt, right? So notice that the slash is right there, right? So the current working directory is normally printed out in the prompt. Also in the title bar, right, it'll also display the current working directory. And we'll just wait for everybody to go by. All right. So I'm now in the current. My current working directory is the root directory. Right. So back to here. All right. Whoa, sorry. Okay. Now it's possible that your version of Bash is not configured this way. So Bash is very configurable, and your terminal is very configurable. So you can configure everything to show you as much or as little information as you want. Right? So if you can't see what the working directory is, there's a command called pwd, right? Print working directory, right? Which if I run that, says that, right, that does generate some output. That tells you what the current working directory is, and it says that we're in the root directory. Okay, so I'm now in the root directory. What do I want to do in the root directory? Well, I might want to know what files are in the root directory, right? That's what the command ls is for, right? ls lists the contents of a directory, right? So if I type ls into your terminal or into a Jupyter cell and run the cell, right? It prints out the list of files and directories that are in the root directory here. Right, so it says there's these files called bin, dev, lib, libx32, and so on and so on and so forth that are in the root directory. Right, the colors are meaningful. Right, so the colors actually correspond to different file types here. Right, anything in blue is a real directory. Anything in green is what's called a link, symbolic link, but we'll talk about those later. Right. So that ls lists the contents of a directory. All right, now. I've just shown you 3 commands, right? CD, pwd, and ls, right? It turns out these commands are actually, they fall into different categories, right? So there are commands that the shell defines itself, right? And so those are called built-ins, right? So if you ever see the term built-in and you're looking at some sort of documentation for Unix or Linux, that means a command that's built into the shell itself. So if you want to know what the built-in commands are, in the shell you can write man built-ins. Man is short for manual, right? And this will describe all of the built-in commands. Now I'm not going to do this in Jupyter because it spits out a huge amount of stuff. So I'm going to do it inside a terminal instead. Right? So here I'm just going to write man built-ins. Press enter and you get this. Right? So this is what's called a man page. Right? Man page is just short for manual. Right? So it's the documentation, or it's one form of documentation for a command. Right? And you'll see that this goes on for a long time. Right? So there's a lot of documentation here. It's very dense. Right? In a few minutes, I'm going to show you how to navigate this thing a little bit more efficiently than that. Right? So for now, I just want to show you that this command exists. Okay, so it turns out cd is a built-in command, right? Now, if you remember or if you know that cd is a built-in command, you can ask for help on the cd command, right? You can type help and then cd. This only works for the built-ins, right? So if I run that, it's going to be messy because, yeah, it is going to be, because I've expanded the font really big, right? It spits out some information on how to use the cd command, right? It tells you what it is too, right? cd, change the shell working directory, right? Yada, 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 right? For the time being, I don't recommend you actually read the man page. Well, I don't recommend you rely on help or man to learn how to use these commands, right? Because the documentation is not written for novices, right? It's not written for people who haven't used the command line before, right? It's all written for people who have used it before and need to remember how to use the command, right? So for now, you should just follow along with the examples and look up anything online if you need to know how to do something specific, right? Later on, so probably in a couple of years when you get used to working in, from the command line, you'll find the man pages and the help pages to be more useful. You can see there's a lot of information, right? It spits out a fair amount. Whoa, sorry. Okay. PWD, that turns out to be another built-in, right? So if you ask for help on PWD, it tells you what it does, print the name of the current working directory, right? And it tells you some other things too, right? PWD is not so bad because it doesn't do that much. It just prints the current working directory, right? Now, if a command is not a built-in, right, then the documentation for the command is probably found in what's called the man page. Right? So to access the man page, the command is man, and then space, and then the name of the command where you want to ask for the documentation for. Right? So if you type man ls, I'm not going to do it here again because it spits out way too much information for Jupyter. I'm going to do it here. Right? Again, you'll see at the very top, what does the command do? Well, it lists the directory contents. Right? How do you use it? There's this little synopsis here. Right? And then a description of all the options and things that this thing will actually do, right? And a lot of these man pages will go on for pages and pages and pages. Yeah?
I was just following along with that laptop.
Yep.
How do you get out of this? I see you have an option to quit. Mine just says BSD and N at the bottom.
Oh, yours. Really?
Yeah.
To quit, press Q. That should work. Yeah?
Yeah.
Okay. All right. Whoa, sorry again. Again, I forgot to ring a mouse, so sorry about that. Okay. So we're in the root directory right now, right? So if I was to draw a picture of the file system, right, you might produce something like this. So there's a root directory, right? Inside that root directory, there's a directory called bin, a directory called home, a directory called root, R-O-O-T, right? Directory called user, and so on and so on and so forth. The standard, the file hierarchy standard actually spells out which directories should be here. Right? So it actually says which of these directories should be here. And I think I list them here for you. Right? So there's a bunch of directories. Each one has its purpose. Right? We don't actually care about what the purpose of all these things is right now. Right? You don't need to know about this right now. You just need to know that these things exist. Right? What you do need to know is that there's something called home. Right? So root slash home, that's the name of the directory that contains your user directory. Right? So all the user directories, they go in this directory called home. I guess you should know about bin too. The bin directory contains most of the commands that we're going to be using in this course. Right? So a command that you type in that's not a built-in is probably in root /bin. All right. Now this ls command, you can actually use it to, so if you just type ls on its own, it lists the contents of the current working directory, right? But with ls, you can tell it to list the contents of a particular directory. So if I wanted to look at what's inside the directory called bin, right, I can type in ls/bin. Right? Not going to do it in Jupyter because, again, it spits out way too much information, right? But in the terminal, if you were to type in ls/bin, it'll spit out a whole whack of files, right? So these are all of the executables, all of the commands, sorry. Not all. These are most of the commands that are available to you from the command line. Right? It's not all of them. It's just most of the it's just most of the ones that this particular Linux distribution decided to put decided to make as standard, quote unquote standard. Right? So they're all in that directory there. You can see there's a lot of them. Right? Okay, so that example there, when I write ls, where's my, okay, so when you write ls/bin, that /bin is what's called an absolute path name. So a path name is just a name of a file that defines the location of the file on your file system. Right? An absolute path name includes all of the directories that lead to the file, right? So here are a bunch of examples, right? So that means all absolute directories, they always begin at root, right? So the name slash, that is the absolute path name of the root directory. Slash bin is the absolute path name of the directory called bin. Slash bin slash ls is the absolute path name of the file called ls, right? ls, that's the command that we've been using, right? So when you type in ls, that's the command that's running. It's the one that's in slash bin. It's the command that's stored in slash bin, right? The notes directory, if you're using the virtual machine, the absolute path of that is slash home slash CISC220 slash big CISC220 slash notes slash bash slash files, right? Slash filesystem.ipynb, right? So that's the absolute path name of this notebook file, right? Now notice the thing about absolute path names you have to type in a lot of stuff to get an absolute path name, right? You can use an absolute path name anywhere you need a path name, right? But normally you don't use absolute path names because there's too much typing involved, right? Ugh, come on. I don't know why they make the scroll bar so small. All right, so normally most of the time you're going to use what's called a relative path name. Right? So a relative path name includes all of the directories to the file starting in the current working directory, right? So right now, in Jupyter, my working directory is slash, right? It's the root directory. So if I want the relative path name of the root directory in Bash or in Unix, it has the funny name period, dot, right? So dot inside a directory means this directory, okay? If I'm inside the root directory, the relative path name of the bin directory is just bin. Right? Slash bin is the absolute path name. Bin is the relative path name. Right? The ls command, if I'm in the root directory, the relative path is bin slash ls. Right? Slash is the directory separator in Unix. Okay, so now I'm going to switch to, I'm going to switch my shell to the directory home slash CISC220, okay? Home slash CISC220 slash capital CISC220. Right, so in my terminal, I'm going to type cd slash home slash CISC220, capital C CISC220. Right? So if I print the current working directory, I am in fact in the big C CISC220 directory, right? Inside the user, whose name is also little c CISC220. Right? Okay. So if I want to get to the parent directory of big C CISC220, the name of the parent directory is dot dot. Right? So cd dot dot. Right? I'm now in slash home slash CISC220. Go back to big C CISC220, right? If I want to find the notes folder, right, that's actually inside the big CISC220 directory. Right, so I'm in the big CISC220 directory right now. If I type in ls, right, you see there's only one file here, and it's called notes, right? So the name notes, when I'm inside the CISC220 directory, that's the relative path name of the notes directory, right? So if I ls notes, right, that will list the contents of the notes directory, right? So inside the notes directory, there's a directory called bash, there's a directory called C, and there's a couple of other things there, right? If I want to find out what's in the bash directory, right, I can use the relative path name notes slash bash, right, and list the contents there. So there are all your notebook files for the bash content of the course. Right? So there I'm using a relative path. Right? So when I do ls notes bash, it's a relative path relative to the current working directory. right? For the absolute path, I would have to type in /home CISC220 big CISC220 notes bash. Right? So relative paths are much shorter. Absolute paths are almost always a lot longer. Right? Any command that takes in a path will probably accept either, unless it's badly written. Right? Certainly all of the standard commands will take in either an absolute path or a relative path. Right? Okay, so this says cd. Oh, so this is not. Is this going to work? Let me try if this works. Command, Control. Okay, so when I change to the home directory, woo, sorry. ls home, good, right? Why did that print out CISC220? Oh, ls, yeah, what's in the home directory? Yes, CISC220, right? So the user CISC220 is in the home directory, right? This is everything. Everything's happening from the root directory right now. So if I list what's inside the USR directory, hopefully I don't regret this. Okay, I don't regret this, good. Right, there's a few directories here. Right, and if I list what's inside the CISC220 directory, right, again using a relative path name, right, I get all of those files there. All right, so that's the difference between relative and absolute paths. Most of the time, you should probably use a relative path. Right? All right, now more about this cd command. Right? So cd on its own, right? Cd is the command that changes directories, right? So cd on its own will change to your home, will change to the current user's home directory, right? So if I type cd on its own, and then I type the command pwd, I should be in the directory CISC220, right? Because that's the name of the user on your virtual machine. Right? Now, the tilde, which is normally in the upper left-hand corner of your keyboard, right? It's the thing that looks like this. Right? That's called a tilde if you don't know that. Right? The tilde is shorthand for the home directory name of the current user. Right? So if you write cd tilde, that's also going to switch to the home directory of the current user. Right? So again, I'm just going to end up in CISC220. Right? The symbol dot on its own represents the name of the current working directory. Right? So if I switch to the home directory, which I'm currently in, print the working directory, that's going to print out home CISC220. If I write cd dot, that does nothing because I'm already in the current directory. Right? So this is just going to print out CISC220 twice. Right? So dot is the name of the current directory. Sometimes you need to use it. Right? And so we'll see examples of that later on. Dot, where is it? Sorry. Okay. Here we go. Okay. So if I'm in the home directory and I do cd dot dot, that's going to move up one directory. So it moves you up to the parent directory. Right? So this is going to print out /home. Right? So it prints out /home CISC220 because that's the current directory here. Right? When I do cd dot dot, that goes up one directory. Right? And I'm now in the parent directory home. Right? And you can do this as many times as you want. Right? So dot dot / dot dot moves up two directories. So it moves up to the grandparent directory. Right? So again, cd on its own, go to the home directory. Cd dot dot / dot dot moves up two directories. So this should take me to the root directory if I run this. Right? So when I do cd on its own, it goes to my home directory, which is CISC220. Dot dot / dot dot goes up two directories. So it goes back up to the root directory. All right. Now, if you've been navigating through the directory structure and you want to go back to the previous working directory, you can type in cd hyphen, cd space hyphen. Hyphen takes you back to the previous directory. Right? So if I switch into the root user directory, right, and then switch to the home directory, and then write cd space hyphen, that should take me back to the root user directory. Right? So if you run that, right, cd user, right, so that takes me to the user directory. Cd takes me to the home directory. Takes me to the user's home directory. And then cd space hyphen takes me back to the previous directory, right? So it takes you back to user. Right? When you do this, notice that when I did cd hyphen, right, I didn't have to print out the working directory again, and it printed it out anyway. Right? So when you use the hyphen, the default behavior is to print out the name of the previous directory and then switch to that directory. Right? If you don't want the name to be printed out, you can use tilde hyphen. Right? So this is the exact same example again, except this time it's not going to tell you where you are at the last time. Right? So now, if I do pwd, I am in fact in the root user directory. All right, so that's how to navigate through your file system using cd and pwd. Okay. If you haven't got it set up yet, try to have your home computer, if you want it set up for Linux, try to have it set up for Monday. Right? Nothing's coming out this weekend, so you've got until Monday to get everything set up.